Autonomous UAV path planning for window detection and traversal, ensuring smooth and safe navigation. Motivation: to enable UAVs to autonomously detect and navigate through circular apertures using vision, ensuring smooth traversal and collision avoidance for effective search and surveillance tasks. Challenges: accurate window detection in dynamic, GPS-denied environments, ensuring smooth trajectory planning for precise UAV traversal. Collision avoidance with safety constraints around the window frame. Objective: to develop a vision-based path planning algorithm for UAVs to detect and navigate through circular windows. To design a smooth trajectory generation using polynomial guidance. Cylindrical control barrier functions. Safe set being a flexible imaginary pipe. The algorithmic architecture begins with the stereo camera, which provides both RGB and depth maps. These inputs are processed to extract the window's center pixel coordinates. The algorithm then checks whether this center is aligned with the UAV's image frame center. If misaligned, a polynomial trajectory is computed to guide the UAV toward the aperture center. If the window is already aligned, a PD-based correction step ensures that the UAV maintains its position within a predefined safe region. The corresponding control inputs are then passed to the energy optimization module, where safety constraints are enforced using the designed cylindrical control barrier functions. Finally, the optimized control commands are sent to the UAV's inner loop controller to achieve smooth and safe navigation. The schematic on the slide illustrates the overall problem setup and the flow of information through the system. The depth camera provides both RGB and depth information. Using the Huff circle transform, the circular aperture is detected, giving its pixel coordinates and radius. Depth values from 4 boundary points are then used, and with the camera intrinsic matrix, the 2-dimensional pixel data is transformed into 3-dimensional real-world coordinates. The aperture center in the body frame is finally obtained and used as the reference for trajectory planning. The polynomial guidance approach ensures a smooth and continuous trajectory for the UAV. A cubic polynomial is used to define the position as a function of time, where the coefficient vectors determine the path shape. The corresponding velocity commands are obtained by differentiating the polynomial, providing time-varying velocity profiles. This formulation enables precise and smooth control of the UAV's motion along the desired path. The safe set is defined as a flexible cylindrical region around the polynomial trajectory, representing the area within which the drone can operate safely. Within this region, the control barrier function, or CBF, maintains a positive value. It becomes 0 at the boundary and negative outside, indicating a potential safety violation. The figure on the slide illustrates this formulation and the concept of safety enforcement using the cylindrical barrier. Numerical simulations were carried out in the Ross Gazebo environment to evaluate trajectory tracking performance. The results show that the quadrotor's lateral and vertical velocities closely follow the generated control inputs. Minimal tracking error is observed in the lateral velocity due to roll coupling, while the vertical velocity demonstrates near-perfect tracking, as illustrated in the figures. Ablation studies were performed by introducing detection biases of 5%, 10%, 30%, and 50%. The bias indicates how far the detected window center is from the actual center. As the drone moves closer, this error naturally reduces, simulating improved detection accuracy. Safe traversal was achieved for biases up to 30%, while a 50% bias resulted in collision, as shown in the figures. The simulation videos demonstrate the drone's smooth traversal using polynomial guidance. The cylindrical control barrier function effectively ensures collision avoidance, maintaining safe passage through the window. The hardware experiments were conducted on a micro-aerial vehicle equipped with an Intel RealSense D435i depth camera and an NVIDIA Jetson Xavier companion computer, with a Pixhawk board handling the control. The results demonstrate smooth and safe traversal of the quadrotor through the aperture, validating the real-world effectiveness of the proposed approach. The experiments were conducted with the facilities provided by Drone Lab Division of AIRL, which is in part funded by the Swayan Initiative of Ministry of Electronics and Information Technology, METI. Additionally, we would like to acknowledge the support of Mr. Sumant A. Gunagi and Mr. Samahith S.A. from AIRL for their support throughout the duration of this project.